Okay, 5.1 is on sequences. Okay, example of sequence. If I have a sub n, okay, is equal to n over n plus 1, n is going to start at 1, and then it's going to continue on. And this is going to be a1, a2, a sub 2, a sub 3, a sub 4, and so on. So the subscript starts at 1 and then continues on with positive integers, okay? Where we'll say n is an element of the natural numbers. Okay, in this case, if I plug 1 in, the terms of the sequence become 1/2, 2/3, 3/4, and 4/5. Okay. B. If I have a sub n is equal to -1 to the nth power times n plus 1 all over 3 to the end. This -1 to the nth term, that's going to be an important piece here. That's going to change the sign. It's going to alternate sign back and forth from positive to negative, positive to negative, positive, negative. That's going to allow us to get alternating sequences and alternating series. Okay, so that -1 to the nth power, again, if n is a positive number, that becomes a positive 1. If it's a even number, it becomes a positive 1. If it's an odd number, it becomes a -1. Okay, so this thing is going to be equal to -1 to the first times 1 plus 1 all over 3. -1 to the second times 2 plus 1 all over 3 squared. And then this is -1 to the third times 3 plus 1 all over 3 cubed. And then -1 to the fourth times 4 plus 1 all over 4 cubed. And then it just goes on forever. If I evaluate the top here, this -1 to the first, that goes to a negative value. And so this becomes -2/3. The -1 squared, that becomes a positive value. And so this becomes positive 3/9. I'll write it as 3/9 right now. You could reduce that to 1/3 if you wanted to. Okay, and then this becomes -1 to the third, which is -1 times 4 over 27. So that's -4/27. And then the next one is positive 5/81. Okay, as we can see, the sign alternates here. Okay, due to that -1 to the nth power. And we call this an alternating sequence. Okay, C, a sub n is equal to cosine to the n pi over 6. Okay, so this becomes cosine to the 1 times pi over 6, cosine to the 2 pi over 6, cosine to the 3 pi over 6, and so on. This becomes cosine of pi over 6, cosine of pi over 3, cosine of pi over 2, and then so on. And this becomes radical 3 over 2, 1/2, 0, and then it keeps going. Okay, so those are some examples of sequences. Okay, put that up here. Examples of sequences. Okay, and so a sequence is just a predictable pattern of values, okay, based on this formula, this equation, a sub n is equal to something. Okay, so definition. Okay, a sequence a sub n has the limit L given as the limit as n goes to infinity of a sub n is equal to L if we can make the terms a sub n as close to L as we like by taking n sufficiently large. Okay, so the more terms I go out, the closer I'm going to get to this L value, this limit. If the limit as n goes to infinity of a sub n exists, we say the sequence converges to L. If the limit as n goes to infinity of a sub n does not exist, sometimes we'll go dne for not does not exist, or tends to infinity, then we say the sequence diverges. Okay, that is the limit as n goes to infinity of a sub n is equal to L if for every epsilon greater than 0, there exists a corresponding integer n capital N such that if the index is greater than capital N, then the term minus the limit is less than epsilon. And basically all this is saying is that as I keep going along this pattern of terms, the terms are getting closer and closer to a certain value L. And if I take one more term, it's going to get me one step closer to L. And eventually it's going to get so close that it will just basically equal L. Okay, so a graph of that looks like if we have, okay, some sort of limiting value here. Okay, we'll say that the limit tends towards 0. Then our first term, A1, would be there. our next term A2, our third term A3, our fourth term A4, and as this gets closer and closer, okay, to 0, okay, we'll go all the way out to AN here. Okay, AN is going to be right here. Well, let me make it a little bit better, easier to see. AN, we'll say that the point AN is there. Okay, that's this distance here. AN is that distance. Okay, let me do this. Let me do A1, 2, 3, 4. This is my A1 up here. A2, A3, A4. This is my A sub n at n. Okay, my limit is this line that it's approaching. That's my limit is that line. It's approaching that line. And okay, for every epsilon, there exists a corresponding integer n. Okay, so that this thing, a sub n minus L, is less than epsilon. Okay, so in order to get epsilon, again, it's kind of hard to see because things are decreasing. In order to get epsilon, I would have to take the next integer after n, and that's going to get me a smaller value that's closer to the limit. And so if you want this to be within, 1/1000th, then I go out to a certain n. If I want it to be within 1/1,000,000th, then I go out to another certain n. And I can always beat it. I can always let this capital N be larger than my little n, and that will always give me a value, okay, an epsilon, okay, such that the differences here, okay, are less than. So I think I have this backward actually. We should have this be n. Sorry about that. So that's n, and then this is epsilon here, because we want this thing to beat out epsilon. Okay, if I go all the way out to capital N, okay, then I can always go one more to lowercase n, and that difference, a sub n minus L, will always be less than epsilon, because as I'm approaching this limit, my values for a sub n are getting smaller and smaller and smaller, closer and closer to that limit. Okay, if we were to kind of blow this up, we could see that, oh, okay, here's the distance epsilon at capital N. And if we go and say this is a sub n, okay, and then this is the limit that it's approaching L, then the distance between a sub n and L is going to be less than the epsilon, which occurred from the previous term. So I can always go out to an n, and then I can go out one more. And then I can go out to n, capital N again, and then I can go out one more. And I can always keep beating my best approximation to this value, and then we basically say that becomes infinitesimally small, and it is the limit at infinity.
By beating, do you mean closer to L?
Yeah, the distance. This thing is getting close. Well, this thing is getting smaller and smaller. The distance is getting smaller and smaller. So the distance between the value and the limit is going to 0, is really what we're saying here.
Okay, thank you.
Yeah. So, I mean, in this case, the limit happened to be, I'm using the limit as 0 in this case, just for simplicity, but it doesn't have to be. We could have, we could have a sequence that goes to a different limit. It's just saying that, look, I'm honing in on this value. And so if I go out to capital N, then I can always go a little bit further to little and lowercase n. Okay, I can always go one extra term, and that's going to get me closer to my limit. And I keep getting closer and closer and closer and closer and closer to the limit. The limit could be 35, could be 2, it could be whatever, but the terms will always get closer and closer, therefore I can always beat out my epsilon. Okay, and then the epsilon is just a small value. Okay, I can take this small value and then I can beat it, and I can get an even smaller value, which is the distance between the value and the limit. Okay, theorem. If the limit as x goes to infinity of f of x is equal to L, and f of n is equal to a sub n, when n is an integer, then we say the limit as n goes to infinity of a sub n is equal to L. Okay, so basically what this is saying, which is kind of nice, if we look at our function, okay, so let's say that we look at our function, let's let the function be, I don't know, f of x equals 1 over x. Okay. Well, if we take those values, those are all the values on this curve. Okay, so all the values on this curve. And if we say, well, we only want the integer values, that's when n is 1, 2, 3, 4. I only want the integer values. I'll put those in black. Okay, I only want the integer values. Well, it's still following the pattern, it's just doing it in jumps. Okay, it's following this f of x function, but it's going in jumps, and so the limit of the function is going to be the same as the limit of the sequence. It just is less values. The only values that we're really counting in the sequence are these black dots. Okay, but it's still going to the same place. It's just doing it with less values. Okay, we're only allowed integer values for x. We say, okay, f sub n is equal to 1 over n in this case. And so the limit as n goes to infinity of 1 over n, okay, was the same as the limit as x goes to infinity of 1 over x. And in this case, this would be 0. Okay, because 1 over 1, the limit as x goes to infinity of 1 over x is 0. So the limits are the same because these points that are derived from integer values, they're going to follow the same path. It's just going to be, there's just going to be less of them, less points than the entire function. We don't need the entire function, but the entire function will go to the same limit, the same L. Okay. Okay, let's do a definition here. Okay, the limit as n goes to infinity of a sub n is equal to infinity means, okay, saying that the limit is infinity, means that for every positive number n, m in this case, there is an integer n, integer n. So for every positive number m, there is an integer n, so a one-to-one correlation, such that if the index n is greater than n, okay, so little n comes after big N, capital N. I know the n and the m's are hard to differentiate, but I'll try my best. I'll try to really emphasize the ums in the m's. Okay. And the in the n's. Okay, so lowercase n is greater than capital N, then we can say that the value of the sequence at lowercase n is greater than m. Okay. What does this look like pictorially? Okay. So before the sequence was converging to some limit, here the sequence is diverging to infinity. And so instead of going and getting closer to some sort of value, it just keeps going up and up and up and up forever. And so this means that if we look at capital N, okay, then that distance to a sub capital N, we're going to call m. Okay, that's that distance. And then we can say that there exists an n after a lowercase n after capital N, such that this thing is bigger. Okay, such that a sub n is a larger value than m. Okay, that height is larger. And we can keep doing this infinitely and say, well, this thing, well, no matter what lowercase n is and what uppercase n is, no matter what those values are, they're arbitrary values. And so this thing will keep going up and up and up forever. Okay, so this keeps increasing forever. Okay. If the limit as n goes to infinity of a sub n is equal to infinity, then we say the sequence diverges okay, to infinity. Okay, the sequence diverges to infinity. Okay, theorem. Our first theorem. Oh no, our second theorem, sorry. Okay. If the limit as n goes to infinity of a sub n is equal to 0, then the limit, or sorry, if the limit as n goes to infinity of the absolute value of a sub n is equal to 0, then the limit as n goes to infinity of the original sequence a sub n also equals 0. Okay. Okay, let's calculate some limits. Okay, so if the, so this is saying that if the limit of the absolute values of each term goes to 0, then the limit of the original sequence goes to 0. Okay. Okay. Okay, let's calculate some limits here. Calculate the limit as n goes to infinity of the natural log of n over n. So natural log of n over n. Okay. So let's look at the function, because this limit is going to be the same as the limit of the function. The limit of the sequence is the same as the limit of the function. So the limit as x goes to infinity of the natural log of x over x. Okay. Okay, well, this is equal to infinity over infinity, which is an indeterminate form. And we can use L'Hopital's rule to help us get that. So this is going to be the limit as x goes to infinity. The derivative of the top is 1 over x. The derivative of the bottom is 1. So this equals the limit as x goes to infinity of 1 over x, which is equal to 0. So since the function has a limit of 0, then the sequence also has a limit of 0. Okay, therefore, the limit as n goes to infinity of the natural log of n over n also equals 0. Okay, number 2. Okay, determine whether the sequence a sub n equals -1 to the n is convergent, which means that it converges to some value, or divergent, which means that it does not exist. The limit does not exist, or it goes off to 0. I'm sorry, it goes off to infinity. Okay, determine this, I should say, whether the sequence is convergent or divergent. Okay, so let's write out the first few terms of this sequence and see what happens. So this becomes, okay, -1 to the 1, -1 squared, -1 cubed, -1 to the 4th, ... Okay, so this is equal to -1, +1, -1, +1, -1. So this thing, all it's doing is, it's just oscillating back and forth between -1 and 1. It's not approaching any real value. Okay, so a sub n does not approach a single value. It keeps bouncing back and forth between 1 and -1. But bounces between 2 values, 1 and -1. So it is divergent. So the sequence is divergent. Okay, number 3. Evaluate the limit, okay, as n goes to infinity of -1 to the nth power all over n. I'll do n minus 1 in this case, if it exists. Okay, let's evaluate this limit. Okay, find out what's the limit of this sequence. This is an alternating sequence. Okay, so what does the alternating sequence look like? It alternates between -1 and +1. Maybe I'll write a few terms over here. Okay, so we're going to get -1 to the 0 over 1. Do this. Okay, and then -1 to the 1 over 2, and then -1 to the 3 or 2 over 3, and then -1 to the 3 over 4, ... Okay, and so this is a sub 1 is equal to -1 to the 0 is +1, so that's 1. -1 to the first is -1, so that's -1/2. Then this becomes +1/3 because it's squared, and then it's -1/4, and then so on. So this thing is bouncing back and forth. It's alternating. Okay. So at 1, we're at 1. And then at 2, we're at 1/2. And then 3, we're -1/2. And then 3, we're at +1/3. And then at 4, we're at -1/4. And so we're kind of bouncing along here. Okay. And so we bounce back and forth. So this is bounce, 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 bounce. Okay, and it's going to keep bouncing, but it's going to get smaller and smaller and smaller and smaller as it bounces. So it's just going to keep alternating, but it's alternating around 0. So hopefully this thing is 0. Well, we have this theorem, okay, that says that if the sequence, the absolute value of the terms of the sequence, if those go to a limit, then the whole thing goes to the same limit. It didn't matter if it alternated or not. So let's take the limit as n goes to infinity of the absolute value of -1 to the n minus 1 all over n. Okay, and that's going to be equal to, if I take the absolute value of each of these terms, I just end up with 1 over n. Okay, the alternating part goes away. That -1 to the n minus 1, it goes away because no matter what we have, whether it's positive or negative, that's all going to go to positive once I take the absolute value. Okay, so these this 1, -1, +1, -1 in the numerator, those are all going to be positives. So this is just going to go to 1 over n. Okay, we'll say the limit as n goes to infinity of 1 over n. And if we evaluate that limit, that goes to 0. So since the limit as n goes to infinity of the absolute value of a sub n equals 0, then the original alternating series or sequence limit as n goes to infinity of a sub n also equals 0. Therefore, These the three little dots, they mean therefore. Okay, that's what they're there for. Okay, therefore, the limit as n goes to infinity of -1 to the n minus 1 all over n is equal to 0. Okay, so that limit is 0. Okay, what does this tell us? This tells us that if a sequence tends towards 0, then its alternating counterpart also tends towards 0. Okay, so it doesn't matter if we make the terms alternating in sign or not, it will still tend towards 0. Okay, theorem. If the limit as n goes to infinity of a sub n is equal to L, and the function f is continuous at L, then the limit as n goes to infinity of the function of the sequence is equal to the function evaluated for the limit. Okay. So if the limit of the sequence goes to L, then the limit of the function of the sequence is f of L. Okay, let's do an example with this. Number 4. Find the limit as n goes to infinity of the sine of pi over n. Okay. So okay, what we can do in this case is we can pull out the sine function and take the limit of the inside pi over n. Okay, that's what this is saying. It's saying we can take the limit of the inside function and then evaluate the sine of that limit. Okay, instead of trying to take the limit of the sine function, which is going to oscillate. The sine function oscillates back and forth. Okay. But we can evaluate the limit by saying, okay, what happens to the value inside the sine function? And then evaluate that. So we can let the sine function here be my f. Okay. So f is equal to the sine function. And say, look, we can say that that this thing, the limit as n goes to infinity of sine of that, is equal to the sine of the limit as n goes to infinity of pi over n. Okay, now this thing is a little easier to evaluate because it doesn't involve the sine function. Okay, this thing goes to 0. So the sine of 0 is 0. So this function goes to 0 at infinity. Okay, even though it keeps bouncing back and forth, it will again kind of peter out. Okay, it will bounce back and forth. It will go like this, and then the function would go like this. Okay, but we're only interested in these values at the integers. Okay, so like what is, so it's, okay, it's getting closer and closer and closer to 0. The sequence r to the nth power is convergent if -1 is less than, as -1 is less than r, okay, or r is less than or equal to +1. So r is bounded between these values, -1 and 1. Okay, the limit, okay, as n goes to infinity of r to the nth is equal to 0 if this thing is between -1 and 1, if r is between -1 and 1, and 1 if r is equal to 1. Okay, if r is equal to 1, then the limit is 1. Okay, but if it's a fraction, okay, then the limit is 0. Okay, if r is a fraction. Okay, or 0. Okay, if it's a fraction or 0, then the limit goes to 0. Definition. A sequence a sub n is called increasing if a sub n is less than a sub n plus 1. Okay, so the previous term is less than the next term for all n greater than or equal to 1. So this is true for all terms. So if the previous term is less than the next term, but that's true for all terms, it's called increasing. Okay. A sequence a sub n is called decreasing if a sub n is greater than a sub n plus 1 for all n greater than or equal to 1. So if the previous term was bigger than the next term, or the next term is smaller than the previous term, and that's always the case, and this thing's going down and it's decreasing. Okay. Okay, so number 5 is a sub n equal to n over n squared plus 1. Is that decreasing?
Decreasing?
Yeah, decreasing. Is this thing decreasing?
Yes.
We want to check it. Okay, we want to check it. Let's check to see if the terms are decreasing. Okay, what does it mean for this to be decreasing? Well, it means that a sub n plus 1, okay, the next term would be smaller than the previous term. Does that make sense? Okay, the next term would be smaller than the previous one. So let's see how we would check this. Okay, I'm gonna put a little question mark here and say, is this true? Is the next term always less than the previous one? Well, what's a sub n plus 1? I'm going to replace the values with n plus 1. N plus 1 over n plus 1 squared plus 1. Is that less than, okay, a sub n, and I'll put this for all n, greater than or equal to 1. Okay, is this less than n over n squared plus 1? Okay, so now what I'm going to do is I'm going to cross multiply and see if this is a true statement. So let's cross multiply. I'm going to get n plus 1 times n squared plus 1. Is that less than n times n plus 1 squared plus 1? Okay, again, this is still a question mark. We don't know yet. Okay, and we need this to be true for all n values. So let me distribute this. This is n squared plus n cubed plus n cubed plus n squared plus n plus 1. Okay, on that side is less than, this is n times n squared plus 2n plus 1 plus 1. This plus 1, that's a 2. And then I distribute the n. So this is n cubed plus n squared plus n plus 1. Is that less than n cubed plus 2n squared plus 2n? Okay, after distributing that. Okay, and I want to okay, I want to subtract n cubed minus n squared minus n minus 1. Okay, or actually maybe I'll leave the 1. Okay, to see if we can compare this. Okay, get a nice comparison. Okay, this is minus n cubed minus n squared minus n. So that goes away. This goes away. And I'm just left with 1 is less than 2. This is n squared plus n. And is that true for all n greater than equal to 1? Is that true for all n greater than equal to 1? We could start with 1 and we could see very, very quickly that this is true. N squared plus n, if n equals 1, then n squared plus n is equal to 2. N equals 2, we get n squared plus n is equal to 6, and then it's just going to keep going bigger and bigger. So this is true. That does check. What does that tell me? It tells me that this thing is decreasing. Okay, therefore, since a sub n plus 1 is less than a sub n for all n, the sequence is decreasing. Another definition.
Could I ask a quick question?
Sure, go ahead.
When you get for all n greater than or equal to 1, where's the 1 come from? Does it just come from like the definition, or?
Yeah, it's how sequences are derived, right? We start with our a sub 1 and then our a sub 2 and then our a sub. So we're just saying that n can't be negative in this case.
Oh, okay. Okay, I understand. Thank
Those
you.
those are indexes. Okay. For all n greater than equal to 1. Okay, the sequence is decreasing. It's just a condition on what the n was, because it is a sequence. Okay, definition, a sequence is monotonic if it is either strictly increasing or strictly decreasing. Okay, next definition. A sequence, A sub n, is bounded above if there is a number n is a number m such that A sub n is less than or equal to m for all n greater than or equal to 1. Just says, look, your terms never get beyond a certain value m. Okay. A sequence A sub n is bounded below if there is a number n m such that A sub n is greater than or equal to m for all n greater than or equal to 1. Okay, theorem. Okay, every bounded monotonic sequence is convergent. Okay, it converges. Okay, so it's saying, look, if you are strictly increasing or you are strictly decreasing, and there is a ceiling m that you can never reach, it's convergent. It's going to converge to something. It may not converge to the ceiling, but it'll converge to something. Okay. If it's bounded and it's strictly increasing, if it's bounded from above and strictly be increasing, then it's going to converge. If it's bounded from below, okay, and it's strictly decreasing, then it's also going to converge. Okay, again, it may not converge to the value m, but it's going to converge to something. Okay, and that is section 5.1.